Hi there, this is Matt Heffernan. Welcome back to my channel. This is the third episode of my tutorial series on Z80 assembly language development, targeting the Sinclair ZX Spectrum to learn how to program a simple system starting at the very lowest level. If you haven't seen the first episode, I strongly encourage you to go back to my channel, and don't forget to subscribe and click the bell to be notified when the next episode comes out, and start this playlist from the beginning. So far in this series, we have learned the basics of assembly language, and went over all of the different addressing modes supported by the Z80. The examples in both episodes consisted of moving data around the spectrum, and now that we have a solid footing in how that is done using all the different addressing modes, let's go a bit deeper and learn about all the specific ways that you can move data. From the beginning, we've been looking at how the load instruction works. The mnemonic syntax is fairly simple, just LD followed by a pair of operands, each with their own addressing mode. The first operand is the destination of a data value, and the second is the source. 1 or 2 bytes will be copied from somewhere and placed at the destination, which will be either a register or a memory address. We've seen all the different registers for the Z80 already, and we know that at least one of the operands of LD needs to reference one of these registers. Some registers are strictly 8-bit, like the accumulator, also known as register A. Some are strictly 16-bit, like SP, the stack pointer, but most of them can either be referenced as 16-bit registers or as 2 separate 8-bit registers, like how the HL register can be split into H and L. All of these registers hold data. Even each of the status bits in the F register can be considered data, but there are only certain ways that this data can be accessed. Accessing the memory of the spectrum is even more restricted, with fewer ways to read and write the data in memory, and in the case of ROM, you can only read from it. Memory is generally the persistent resting place of data, which means that a large part of every program is getting data from memory into the registers, processed, and then written back out to memory. Data can also move to the Z80 with hardware ports to interact with input-output devices. We'll get into how this works in detail in a later episode, but for now it's good to be aware that data is coming into the system often through one of these hardware ports, most often by using the keyboard, but also from the tape input or other peripherals. Then data can be output from the Z80 to other devices in the spectrum, like the tape output or the piezoelectric beeper, as well as external peripherals like printers. All of this is done with hardware ports that are addressed separately from memory. But for this lesson, we are just going to stick to memory and see how all this works another time. Let's get back to that load instruction. We've seen how the operands work, and all of the addressing modes supported by each of them adds up to a staggering 184 opcodes in the Z80 instruction set architecture. That's nearly a quarter of all the opcodes, but LD takes on a lot of responsibility. The simplest and fastest LD opcodes are for moving data between pairs of 8-bit registers. There are 13 different 8-bit registers, but you can't move data between any pair of them with a single load instruction. As you can see in this table, the I and R registers can only be paired with A, while the upper and lower halves of each index register can't be paired with H, L, or the halves of the other index register. Even with these limitations, we still end up with 101 different opcodes for doing these 8-bit copies between registers. All of these opcodes are a single byte and can be executed very quickly. There were fewer loads supported between 16-bit registers, with only 3 opcodes available, each used to load the stack pointer with a new address, which could be an HL or either of the index registers. You can load immediate values into most registers, with 8-bit values getting loaded directly into everything except I and R, which both require you to load the value into A first. That's not a big deal, as programs rarely need to do that more than once. You can also load an immediate value into memory by putting the address into HL and using register indirect mode, or using the index registers and loading the value into an offset from one of those addresses. Extended immediate loads are supported to get 16-bit values into all of the 16-bit registers, except for the program counter. Of course, you load a value into the program counter by doing a jump, so it doesn't need to be done with a separate load instruction as well. 8-bit values from memory can only be directly loaded to A, but you can load 2 bytes from memory into any 16-bit register, except, again, for the program counter. In that case, you'd have to do an indirect jump with HL or an index register, and we'll see how that works in another lesson. Going the other way, we can write data to memory using the same registers, with the operands reversed. Single bytes can only be loaded from A, but 2 bytes can be loaded from any 16-bit register except the program counter. Needing to write the current value of the program counter to memory is pretty rare, but you could do it through some shenanigans with the stack. We won't get into how that works until a later video either. LD supports register in direct mode for both operands, but only when paired with just a register. You can use BC or DE to hold memory addresses, and load a byte from memory into A, but not into any other registers. If you use HL, you can load a byte into A, B, C, D, E, and even H and L. Going the other way, you can write the value in A to the addresses in BC or DE. If your destination is the address in HL, you can load the values from registers A, B, C, D, E, and yet again, H and L, just in case you need to get half of the address written to that address. I'm at a loss as to why anybody would want to do that, but if you have an idea, or better yet an example, please share it in the comments. Finally, we get to the last mode supported by load, indexed addressing. You can use indexed addressing in all the same cases as using indirect HL, with either IX or IY. A, B, C, D, E, H, and L can be used for reading or writing data in memory using offsets from either IX or IY. The exchange instruction, or EX for short, transfers 16-bit values between 2 locations. They actually exchange values, as the name suggests, rather than copying from one to the other. There are 5 different opcodes for EX, starting with EX AF AF prime, which will exchange the current accumulator and status bit values with the alternate A and F registers. The values in the alternate registers will not have changed since the last exchange, so this can be a good way of preserving state without growing the stack. You can also exchange the values between DE and HL, which comes in very handy as HL has so many more uses. The rest of the opcodes are all for exchanging register values with the top 2 bytes on the stack, that is, whatever was pushed most recently. These are some of the shenanigans I was talking about earlier. Don't go messing with the stack unless you really know what you're doing. We'll have a whole episode in this series on the stack, which should provide that knowledge. The exchange instruction with 2 X's, EXX, is used for exchanging BC, DE, and HL with their alternate registers. Like the EX exchange, this is the only way to change the values in these alternate registers. They will have the same value since the last EXX. You don't need any operands, as EXX will exchange all 3 pairs of registers every time. To illustrate how the exchange registers work, let's go through a little case study in using alternate registers. In this table, we see a program with each instruction followed by the values in each of the affected registers after the instruction has been executed. At the beginning, the values are all unknown, and we will follow the program as it sets values in not only the main registers, but also in the alternate registers. As we have seen earlier, the only way to affect the values in alternate registers is through the use of exchange instructions. And now we'll see exactly what happens. First, we load A with the value 42, so that's the only register that has a known value at this point. Then we do an AF exchange, which puts the 42 in the alternate accumulator, and the irregular accumulator now has whatever mystery value was in the alternate A previously. Doing another immediate load into A, this time with 57, sets the value in the main accumulator, while the alternate one still has 42. We do another AF exchange, and you can see they switch values, with 42 back in the main and 57 now in the alternate A. Next, we load up BC, DE, and HL with 6,502, 768, and 22,528, respectively. Then we do an EXX, and that puts those values in the alternate BC, DE, and HL registers, and the main registers now have unknown values that were in the alternate registers previously. Then we load up BC, DE, and HL again, but this time with 8,080, 6,144, and 16,384, respectively. Now all the registers have known values, so that when we do another EXX, we get the previous values into the main BC, DE, and HL registers, and the new values in the alternate registers. Regular load instructions may not be able to copy one memory value to another directly, but there are other instructions that do that, and they help make it easy to move data around memory with very little code. First up is the load increment, or LDI instruction. It has no arguments, but expects that the registers it uses to have been preloaded. It copies a byte from the address in HL to the address in DE. Then it increments both DE and HL so that they will point to the next addresses. It also decrements BC, which you could use as a loop index that's preloaded with the number of bytes to copy. Then you could just keep executing LDI and then checking BC to get down to 0. But if that's all your loop needs to do, then you can just use, wait for it, LDIR, or load increment repeat. This single instruction will copy a whole block of data, using the value preloaded into BC as the size. When it's done, and it could take a relatively long time, the entire block of data will be copied. BC will be 0, and DE and HL will now be pointing to the bytes after their respective blocks. This fits a lot of functionality into a single 2-byte opcode and does its task as quickly as possible. Here we can see the code required to copy a block of data, in this case implementing double buffered graphics. We set up an alternate screen memory at hex E1000, which we could render graphics in before it becomes visible in the actual screen memory at hex 4000. So once we are done rendering, we can just copy the whole block with these 4 instructions. We load BC with the block size, which is 6,912 bytes to include both the bitmap and the color attributes. We put the destination address in DE, and then the source address in HL. Then we just do an LDIR, and after a mere 145,147 t-states, or 41.47 milliseconds at 3.5 megahertz, we can move on to the next instruction. Of course, with a 50 Hz PAL display, that means we can't do this every frame, as just over 2 frames would go by in that time. So once we get into graphics in this series, we'll look into some other strategies. If you want to copy data in memory going in a backwards direction, you can do this with LDD, or load decrement. In this instruction, DE and HL are decremented instead of incremented, so you want to preload them with the highest addresses you want to copy between. BC is still decremented too, so you can use that in the same way as with LDI. And of course, if your copy loop doesn't need to do anything else, the Z80 still has you covered. LDDR, or load decrement repeat, will do that backwards copy loop in a single instruction. It takes exactly as long as an LDIR instruction copying the same data, but depending on how your program and data modeler is structured, this may be a better option requiring less code to set up. Here we see another approach to doing that same double buffer copying, but this time with LDDR. We still put the same value in BC, but put the last addresses in the data blocks into DE and HL. Then after LDDR is done, BC will be 0, and DE will have decremented 1 past the beginning address hex 4000 and end up at hex 3 FFF. Similarly, HL will go back past hex E1000 and contain hex D FFF at the end. For our example program, we're going to use all of these instructions to create some data and move it around. It won't be a very useful program, but it should help you to see what happens when all of these instructions are working to produce this colorful pattern you see here. We start our code again with the device macro saying that we're targeting a 48K spectrum, then an ORG statement that will make our code start at hex 8000. We start by loading a bit pattern of binary 11001100 into the accumulator, which will give us a 2-pixel wide stripe pattern when written to the screen bitmap memory. To do this, we put the starting address of the bitmap, hex 4000, into DE, and then load that pattern to that address, which will put it in the first 8 pixels on the top row of the display. We exchange DE and HL so that HL now has that address, and we load up DE now with the next address, hex 4001. Then we load BC with hex 200, which is the number of bytes in 16 rows of pixels. Next, we have a label for the start of a loop to fill in 16 rows of the bitmap. With DE 1 byte ahead of HL, this will mean that the bitmap value we already have loaded into the first byte will be copied to the following bytes of memory with each LDI instruction, which then increments HL and DE. So HL will always be pointing to the last value copied. Rather than doing an LDIR, We follow the LDI with a load of B into A, and then a bitwise OR with the value in C. If BC was 0, then the Z bit should be set after the OR instruction. So if Z is not set, we jump back to the top of the loop. Once BC gets down to 0, we know that all 16 rows have been filled with the same value, and we fall out of the loop. Now, this doesn't mean that the first 16 rows on the display now have this bit pattern in them. The way that the Spectrum screen in memory works, the first 8 rows in the address space are actually 8 pixels apart, and then we go back to the second row of pixels and start filling in every 8 rows from there. This will effectively give us 2x2 pixel squares on the first 2 lines of the display, and then continuing on at the 9th and 10th rows, etc., until we have 8 rows of squares with 6 pixel gaps between them. We'll get into how this works in detail in a later episode, so for now just understand that this isn't a traditional bitmap layout. That's okay, because it doesn't really matter when we're just concerned about placing a pattern in memory. Putting it in screen memory just gives us an immediate visualization of that data pattern. Anyway, once we're out of the loop, HL is now pointing to the last byte that was written, which is actually the beginning of the 17th pixel row in memory, or the 3rd row on the screen, however you want to look at it. Now we want to shift that pattern to the right, making the pattern centered in each byte, a nice symmetrical binary 011001110. We can make that change right in memory by doing a logical shift right instruction with the register indirect mode on the address in HL. We load up BC with hex 200 again, and this time just do an LDIR. This will write out another 16 rows of pixels, this time with the new symmetrical pattern. Those little squares we had before will now have more squares underneath them, just shifted to the right by a pixel, effectively making little backslashes that are 4 pixels high and 8 rows with 4 pixel gaps between them. We then shift the new last byte at the address in HL, which will now have the pattern shifted to the right with binary 0110011. Then we load hex 45FF into DE to get the last byte of the next 16-row block. A single LDD will copy the new pattern to that last byte. Then we set BC to hex 1FE, as we already have the first and last bytes in this block set, so we only need to fill in the middle. We load HL with hex 45FF, as DE should now be pointing to the address before, due to being decremented by the LDD. Now we can do an LDDR to fill in those bytes in between, and our backslashes have grown to have 3 squares each with only 2 pixel gaps between them. Now we want to fill in the 4th block, and fill all those gaps to make giant backslashes going across the top 64 pixels of the display. So we load hex 4600 into HL to get the first address of this block, and then load the final pattern right into that memory byte. It's another symmetrical one, binary 100110001. This will connect the last pattern to the first one to make contiguous backslashes. So we then put the next memory address, hex 4601, into DE, and the number of remaining bytes to write into BC, which is hex 1FF because we don't want to go past the end anymore. We could just do the LDIR right now, but instead we'll do an EXX and save these 3 values in the alternate registers. Now we can move on to setting the color attributes. We load up HL with a new address, this time hex 5800 for the first byte of color attribute memory. Then we load the address with the first color we want for the upper left corner of the display, which is blue ink on black paper. We set DE to the address of the next byte, hex 5801. Then we set BC to hex FF, as that will get us through the first 8 rows of color attributes, which will cover the top 64 rows of pixels on the display. Remember, the color attributes are for 8x8 tiles across the display, so we only need 1/8 of the memory needed for the bitmap memory to cover the same area. We start the color loop with an LDI to copy a byte and increment HL to the next address, which will be the address the DE was at going in. So incrementing the value at the address in HL will change the ink color of the value we just wrote. We want to keep the black paper color, so if our increment made the ink color in the lowest 3-bit 0, we know that the increment carried up into the paper bits, so it's time to reset the color. To detect this, we load A with 7, which will set the lower 3 bits in the accumulator. Then we do a bitwise AND with the color value, which will set the Z flag if those 3 ink bits of the color value are clear. If the Z flag was not set, then we know the ink value is still non-zero, so we jump ahead to the next label. Otherwise, We reset the color value to the initial blue and black color, and then continue on to next. There we want to see if BC is down to 0 yet. So again we load the value of B into A, and then OR it with C. If the Z flag wasn't set, then BC is still non-zero, and we jump back to the beginning of the color loop. Once BC gets down to 0, we do another EXX and get those register values we set up earlier and stashed in the alternate registers back in the regular BC, DE, and HL registers. Now we can just go ahead and do the LDIR finally, and we're done. So we can just return back to whatever called our program. To deploy our code, we use the SaveSNA macro to create a snapshot file called data.sna. We have a build script too. Like last time, we just need to call sjasm plus with the --lst flag to generate a listing, and then the file name of our assembly code, data.asm. That's it, so all we have to do now is run it. Let's run build.sh, and we'll check the directory listing, and we can see that data.sna was generated, so now it's time to run it in the emulator. This time we'll try using Fuse. To load our snapshot, we hit F3 and select data.sna. And there's our expected output, a nice thick row of nice thick backslashes in all different colors. If you look at the display, it almost seems like our color tiles are tilted, which is pretty neat. But most importantly, we can see how our efforts to use all the different ways to move data around can get real results, and some of the nice shortcuts that the Z80 provides you for accomplishing this. That's all we have for this lesson. Next time, we're going to look deeper into how conditional instructions work and give us the ability to control the flow of our program, just like we've done in the last 2 episodes by using the Z bit to do conditional jumping. There are a lot more conditions and instructions that you can use, and we'll get into all of them when you come back for that lesson. Please subscribe to my channel and click the bell to be notified when the next episode comes out. And please like this video if you learned anything, and let YouTube know that you want to see more tutorials like this. If you can't wait for the next episode to go public, join our Patreon community and see my videos ad-free as soon as they are uploaded, just like the people you see here. Thanks for watching, and I hope to see you again soon. Bye-bye.